Hello again, everybody. I want to give us a basic overview of chemistry, and while this PowerPoint seems rather long, we're going to try to hit on some main points and just use the rest of it as illustration. So don't be too worried. So let's start off with matter. Well, why does this matter? Sorry, bad joke. The point of knowing the chemistry, even though you're in a biology course, is that biology is made up of chemistry, and chemistry is made up of physics, and all of that, of course, requires math. And so one of the things I want to get across to you is that matter is what our bodies are made of, is what our dogs, our cats, our plants, our food is made of. So it's anything that occupies space and has mass. Matter may exist in a few different states. You're probably very familiar with solids, liquids, and gases. I won't go into great detail there. Matter may be changed. You can do so either physically, but that doesn't change the way that it functions. Like, so if it's still a solid, it'll stay a solid. Well, that's not quite true. You can go from solid to liquids, I guess, but you're not going to change that solid from mercury to gold, for example. So does that, hope that makes sense, that you're going to stay the same thing. Chemical changes, on the other hand, will actually change the chemical composition. You're actually changing the essence of what that series of particles are put together, how they're put together, and how they function. Energy is separate from matter. It's the ability to do work. So you have matter that has mass, and mass and energy are separate things, but they do interact. Energy itself has no mass. It just takes up no space. Therefore, we can't make energy. We can make molecules that store energy, for example. And so you have things that have kinetic energy, where energy is actively doing something, in this case work. And you have potential energy, where it's inactive or stored. And a lot of times our bodies are storing this, but in the process of doing the work to store. So you have both kinetic and potential both taking place in the body. So the different forms of energy we might see: the chemical energy stored in chemical bonds, electrical energy results from the movement of charged particles, especially talking about electrons here. And yes, bodies do have electrical currents. Mechanical energy is energy directly involved in moving matter, and of course we move ourselves, so we have mechanical energy. And radiant energy travels in waves, energy of the electromagnetic spectrum. Do we do that? Absolutely. We give off heat, for example, and that's energy that is radiated. Now, a very important molecule that you really need to know is ATP. And while you probably don't need to know it for everyday life, knowing that there is a single molecule that acts kind of like the currency of a cell throughout all of our body that holds on to energy is really important. And it's not because the ATP, or adenosine triphosphate, actually is energy, but the bonds that hold it together contain energy. So what happens if you were to break a bond? You release energy. What happens if you form a bond? You store energy. Now, the elements of our matter are, there's a lot. There's 96% of our body made up of 4, but there's other ones that are also used in micro amounts. I do want you to know these 4. Of all the ones that can be in our body or make up the living world, these 4 kind of make the world go round. So we have oxygen. It's our most common. 65% of our body's mass is made of oxygen. Our molecules are actually carbon based, so a lot of the molecules, especially if they're organic molecules, they're going to have carbon as their main atom at the middle, sometimes more than one carbon. Hydrogen will be to the periphery of that, and nitrogen will be involved at different places. Okay, so know those 4. So we've got our oxygen, carbon, hydrogen, and nitrogen, and here's some illustration. Feel free to look at this. You'll see some of this information come later, so I'm not going to go into it in great detail now. Some things that you use in lesser amounts but are probably familiar with: calcium, phosphorus, potassium, sulfur. Used in so many different things. You can explore the table. sodium, chlorine, magnesium, iodine, iron, for example. And there's even trace elements, maybe you've heard that term: chromium, cobalt, copper, fluorine, manganese, molybdenum, that one's just my favorite to say, selenium, silicon, tin, and vanadium, and zinc. You don't have to know the trace elements, or these, basically anything other than the four are not something I'm going to specifically ask you about. So I've mentioned the term atom at the bottom, at the base I should say, of our molecules. It's the building block of our molecules. Atoms of elements differ from one another, and that's how we know that one molecule is different from another. The atomic symbol, you can see, is a chemical shorthand, and we'll see things like S or H, N, for example, that represent things. In these atoms, you're going to have protons, neutrons, and electrons. Protons are positive, neutrons are neutral, electrons are negative. I think we're probably all familiar with that at this point. One really interesting thing to note is that electrons have very, very, very little mass, and almost negligible when we actually take into account the mass of these atoms. So all atoms are electrically neutral. So you should have the same number of protons as electrons, and these things keep the atom neutral. They cancel each other out. Ions are atoms that have lost or gained electrons. Notice it's not lost or gained neutrons or protons, it's just electrons. Okay, so ions are things that are either positive or negative because they've either lost electrons or gained electrons. There is a planetary model of this, and I think it'd be easier if I just show you. So you've got your protons in the red and the neutrons in the yellow here in the middle, and then you've got this orbiting amount of electrons that go around this nucleus. Okay, and this is one of your basic ones, well, the most basic. This is one of the most basic, I should say. Helium. Hydrogen's a little, it's got one proton, one neutron. So that's pretty simple, and of course you can have more orbitals that go outside of these two. We won't get into that since this is not chemistry. But this orbital model is where the electrons actually interact with other atoms, and so you can share, or you can remove, as we've seen, or add electrons, and it's in these orbitals that the interaction takes place when we do chemical reactions. So here's helium again. Not sure why I put that extra helium picture in there. Electrons determine a atom's chemical behavior and its bonding properties, as I was saying. The planetary model is not quite right. I mean, they're not like necessarily staying in a line going around. They're more of this area, not a disk necessarily floating around. It's kind of a three-dimensional idea. We want to keep that in mind. So we kind of show it. Let me go back real quick and just show you. We kind of simply show it, and I see the reason why I put this in here now. This is more of a, cloud of electrons as opposed to just this string that go around. Okay, not important for us too much right now, but just realize that sometimes we explain this a little more simply than it really is. Now, to know what element you've got, you need to know the atomic number, the atomic mass, and the atomic weight. Now, I'm not going to ask you these things too much on the test, okay? So don't worry about this. There's some very key things that I do want you to know, okay? So I'm not going to ask you an atom's number, atomic number, or mass number, or their weight. But I do want you to know that there are numbers associated with the atoms, and sometimes it's easy to remember those things because of the way the periodic table is set up to help us remember. And that helps you to know how many protons are at the middle of that atom, in that nucleus. So every atom has a specific number of protons. And that can indirectly tell us the number of electrons, assuming it's not an ion. Now, we get a different number with the atomic mass when you include the nucleus, which has the proton and the neutrons, and usually for every proton you've also got a neutron, so it's they're usually equal amounts. And then the atomic weight will take into account all of this. And this is where I wanted to kind of point things out. Isotopes. Okay, so here's hydrogen, for example. You've got one nucleus, one proton in the middle and an electron floating around. We've got 2 protons for helium, 2 neutrons, and 2 electrons, and then you can see there's 3 here of each proton and neutron with your lithium, so for example. So the numbers are associated. Isotopes are a little bit different. This is where you have the same number of protons and electrons, but you have a different number of neutrons. And sometimes you can get these different isotopes. And so, for example, carbon-14 is one where we can see the kind of isotope of carbon in a living or dead tissue that's, relatively not been dead too long. We can actually get an idea of how old something is based on the relative abundance of those isotopes for carbon-14. And we use other isotopes for kind of radioactive dating, other parts of like geology, for example. Okay, and here we've got some examples of hydrogen, where we've got hydrogen with no neutron, hydrogen with a neutron, and hydrogen with 2 neutrons. So hydrogen, deuterium, and tritium. So when you see things like calcium, you'll see a symbol Ca, and basically 20 is its atomic number. Now that will also help us to figure out the number of electrons in the shells on the outside of the orbitals. We're not going to get into that, but know that those outside electrons are the ones that interact. I've kind of mentioned radioisotopes. This is like a really heavy isotope of certain atoms, and because it's unstable, we can actually measure how quickly it degrades, and we can use it to tag and trace biological molecules even through the body, which is really kind of cool. Now molecule, I've used this word a few times. This is where you've got 2 or more atoms of the same element combined. So 2 hydrogens together make H2, which is a hydrogen molecule as opposed to a hydrogen atom. Hydrogen molecule is the gas that floats around. Okay. Now this is a basic chemical equation, and the 2 hydrogens on the left are the reactants, and on the right we have the product. And that arrow says yield. So we've got 1 hydrogen atom plus another hydrogen atom yields the product of hydrogen 2 gas. So, compounds are 2 or more atoms of a different element combined to chemically form a molecule. So we've got hydrogen and carbon in this example. We've got 4 hydrogens, 1 carbon, and those carbons have 4 bonds. That means that outer I thought I had a picture, but I don't. Outer shell of electrons, there are 4 open spaces, so it can share electrons with the hydrogen 4 times, and so we can do 4 hydrogens combined here, and this gives us methane. Sodium plus chlorine will give you table salt, sodium chloride. That's one chemical reaction that we may be maybe not familiar in it happening, but familiar with the product. Chemical reactions occur all the time. They occur when atoms combine with or dissociate from other atoms, and their chemical bonds are energy relationships involving interactions among the electrons. So those bonds, as I've said before, are where the energy is found. So when you create bonds, you're storing energy. You may lose a little bit of it in the process, but you stored a lot of it. Or when you break bonds, you release the energy to go use for something else, and also some of that energy will be lost. That's called heat, by the way. When you lose energy, that's not useful for anything else. So electrons are in these outer shells, and they're the ones on the very far outer part of the orbitals are the ones that interact with other atoms containing electrons. So it's the distant electrons furthest from the nucleus that are the ones who are usually going to interact. You have different shells. I'm not going to go into those, don't worry about that. But it's the outer shells that I want to get at it, and these are called valence shells. So if you ever see the term valence, Those are the orbital on the outside where atoms will interact with their electrons. Sometimes you can have a full valence shell, and there are what's called the noble gases, the ones on the far right of your periodic table, that do not have any interaction with other things because they have no electron no space, I should say, for electrons to interact, to share. So noble gases are basically considered to be inert. They are unreactive. So neon, for example, is one of those. You see 8, and usually it's 8. 1, 2, 3, 4, 5, 6, 7, 8. Full set of valence electrons here. Helium is inert as well, so it's got a full 2. So this is why you have the different orbitals. They have different amounts. It's 2 at the beginning and usually 8 afterwards. That for all the other orbitals. Don't worry about that. You don't have to know it. We do talk about the 8 here, and so sometimes you can, like I said, I'm not going to be making you test on this, but I do want you to recognize that it's those 8 on the outside that interact. That's the valence shell. And sometimes if I know the place in the periodic table, I can tell you how many spaces are open in that shell. So for example, carbon, I know, has 4 electrons in its outer shell, and since 4 and 8, so 8 minus 4 gives you 4, you need to have 4 more spaces, and that's how I knew that hydrogen would have 4 hydrogens to take those 4 spaces, because I know how many bonds that are allowed to be made through this rule of 8. So we get reactive elements if you can gain or lose or share electrons when you have less than 8 in your outer orbitals. Okay, so look at carbon. There's 4 instead of 8, so I know we can make 4 bonds. Hydrogen has 1 there. It usually should have 2, even though in this case it doesn't make sense. Since hydrogen has 1 proton, you would expect it to have 1 electron, which it does. But because those outer valence valence shells can have more hydrogen bonds, electrons that will make bonds, then that's why hydrogen is very reactive. So if hydrogen and oxygen come anywhere near the presence of each other, you're going to make water, and you're probably going to do it explosively. If you've heard of the Hindenburg, go look that up. You'll see what I'm getting at. Okay, now let's talk about the kinds of bonds. This is rather important, so I do want you to know ionic bonds and covalent bonds. Ionic bonds are when electrons are completely transferred from one atom to another, where these atoms are going to be relatively stable, and we're going to get this transfer to kind of relieve the amount of numbers on those outer orbitals. So for example, carbon's got 4. If it were to make an ionic bond, it might pull 4 electrons from somewhere else. Not share, but pull, or to give its 4. Now, not everything does ionic bonds, so carbon actually doesn't do that, as far as I've ever seen. But there are some atoms that can do this, and so they actually take away electrons or give electrons. And this is where you get something called ions. Again, remember, if you don't have the same number of electrons as you do protons in the nucleus, then you're not going to have a neutral molecule. You'll have something positive or negative. So an anion is something with a negative charge because it's gained more electrons than it has protons. Cations are positively charged, and they are positive because they've lost electrons, and that's fewer electrons than they have protons. Basically, the proton is over, its charge matters more because there's more of them. Okay, now things that give their electrons and things that take their electrons, they usually stay in association with one another, creating ionic bonds. So sodium and chlorine are a very good example of this. Chlorine will gain, an electron from that single sodium outer valence shell, and that means sodium will actually be a little bit positive and chlorine will then become a little bit negative, and because positive and negatives are attracting to each other, they associate into an ionic bond and hang out. Covalent bonds are different. These are where atoms bond through shared electrons and they really stay snug and tight with one another. So they're shared usually in pairs. You can have single covalent bonds where you share one pair of electrons, and you can have double where you share two pairs of electrons. Hydrogen and hydrogen coming together gives us hydrogen gas. Okay, and this, if we keep in mind that the outer valence shell here should be 2, hydrogen on the right gets to share the one that it has and the other one from this hydrogen, so it has now kind of 2 that it's getting to make use of. Same thing for the other one, it's getting to kind of hold on to the one it has but also share the other one, so they kind of get that balance to kind of make them neutral. Here we've got oxygen sharing 2 to give us oxygen gas. Now you see that they're sharing 2 pairs. Here we've got this double bond represented over here. By the way, we write O with this double bond O. So you can actually represent that in your diagrams. Here's carbon doing 4 single bonds. 1, 2, 3, 4. Okay. Now covalent bonds can also be broken into a couple of groups, polar and nonpolar. Nonpolar covalent bonds are going to be shared equally between the atoms of the molecule, and so you get an electrically neutral molecule like carbon dioxide, for example. Here we've got, when I say equal, notice there's this kind of straight line of orientation. We've got one O on this side, one O on that side. They're even on each other. It's hard for me to describe this because I kind of intuitively understand, but imagine this was on a string. These would be completely balanced with each other on a straight line of that string. Okay, there's no bend in that string. Now that's what happens when you've got polar covalent bonds and you get unequal sharing between these atoms. And so what you get is something like a pole. You get a positive side and a negative side, and water's a great example. So this is still 3 atoms like we saw with carbon dioxide, but what happens is, with the way this attaches, is the red oxygen and the 2 hydrogens that attach don't attach equally. Notice they're not straight across from each other. If this was on a string, basically you would have to have a third hand kind of, if you're holding this string straight across, you'd have to have a third hand kind of pulling it and making a triangle. I'm not sure if that makes as much sense as I was hoping. But let me see if I can draw something that makes sense. So you'd have your oxygen, you'd have your hydrogens. Okay, so this is not a straight line, the way these are connected. Okay, which I know is exactly what's over here, but I think sometimes showing it this way makes more sense. So what you end up with was a slightly negative side and a slightly positive side, and because you now have a little bit of charge, you can get something out of that called hydrogen bonds, where these things, they're very weak, but you can actually have things like water holding to itself. So you've got a negative side over here and you've got a positive side over here, and let's say you have another water. Guess what? It's going to orient this way because this is positive, this is negative, and the positive from the hydrogen and the negative from the oxygen are going to hang out kind of together. If you were to throw another water in here, guess what? It's going to orient the same direction. Okay, it's not going to be flip-flopped with positive hydrogens here, the blue side touching. It's going to be red blue, red blue, red blue, in that order. And this is going to create that thing called hydrogen bonds. So it helps to kind of orient some of these molecules together because you have a little bit of polarity. This is why water sticks together. If you've ever noticed that there's water tension, you know, water bugs can run across the top of water because there's actually some tension across that water that's a little bit solid-like, as opposed to us thinking of it as a liquid. If you ever get water on the like a water drop on the tip of your finger and you kind of like move your hand down, you see the water drop kind of pull away and then pull back up. That's an example of this surface tension of water having polarity and hydrogen bonds kind of holding it together. Proteins do this too inside of our bodies. Hydrogen bonds are extremely important. So here's an example of that water bug being able to kind of stand on the water because there's actually some tension there. Now we don't stand on water because we overcome that tension. We're too heavy.